Once again, welcome you to another series of our lectures. And in this series of our lectures, we'll look at molecular hybridization. So we've looked at chemical bonding with regards to Lewis Dots theory. So we've looked at chemical bonding. We've also predicted the structure using that theory. Now what we'll do is we'll move and talk about molecular hybridization and how molecular hybridization can be used to determine the chemical bondings, then later on to determine the shape of the molecule. Then one thing that you note is that in hybridization, it involves orbitals. We'll get to understand that in details as we continue. Now, just a quick recap. We used the repulsion theory to predict the shape of the molecule based on the Lewis's approach. But now what we'll do is that we'll move to use hybridization to explain molecular bonding and the shape of the molecule. Now, the most important thing to do now is to explain what hybridization is. Now, hybridization, you combine two valence atomic orbitals. Now, the question one might ask is, what are valence atomic orbitals? Valence atomic orbitals are orbitals that have valence electron. Then the valence electrons are the ones that are in a highest principal quantum number. Now, just to explain this further, let's take, for example, carbon. Drawing the electronic configuration of carbon, you have 1s2, 2s2, and 2p2. So when you talk about valence electrons, carbon has 4 valence electrons because it's in group 3. So what it means is that the valence electrons are in the p and the s. So making these two to be 2 valence atomic orbitals. And the other thing that you can note is that valence atomic orbitals are just basically in the outermost shell, which is just basically the one having the highest principal quantum numbers. Then after we then now what you get is that these hybrid orbitals will be responsible for molecular bonding, which we'll discuss at length. Then they'll also be very important in this determining or predicting the geometry of the molecule. Let's start with molecular bonding. Now, before we go into details with molecular bonding, there's one key concept that we have to understand is what you know as a sigma bond. So now what you get is that if you have 2 valence atomic orbitals combine or overlap, they form what you normally refer to as a sigma bond. Now the question is, what is a sigma bond? A sigma bond, abbreviated with the letter phi, is a bond that is formed by overlapping of atomic orbitals using to a end-to-end fashion. So orbitals will overlap using an end-to-end fashion. We'll get to see that as we proceed. Then what you get is that now the electron density will be between the 2 nuclei of the bonding atoms. So when you talk about a sigma bonding, overlap is end-to-end. So if someone asks you, what's a sigma bond? A sigma bond is a bond that is formed by overlapping 2 atomic orbitals by end-to-end fashion. Full stop. Now, let's start looking at what overlap is. We'll start with an SS overlap. And the best example of an SS overlap is the hydrogen molecule. So a hydrogen molecule is formed by 2 atomic hydrogens overlapping to give you a hydrogen molecule. Then when you look at the geometry, you know that an S is spherical. So you have 2s and another s. So what you get, one will have an electron with a clockwise spin and the other one of an electron with an clockwise spin. Then these two overlap on end to end, which will be kind of difficult to see because these orbitals are basically circular. And what they give you is this. This is what you now refer to as a sigma bond. Then in the sigma bond, you have an electron density is concentrated in the center between two atoms. And this is what you basically form. So what you have is that you have this will overlap with that, this will overlap with that, then they'll fuse together like this to give you molecular orbital. Now this we can also move to what you normally refer to as an sp, right? Now note, for a bond to take place, an atomic orbital should have one electron and the other one should have one electron. Then the two now can share those two electrons in the orbitals. And how do they share those electrons? The orbitals basically will overlap. So another example that you can get is that you have a 1s and a 3p. So a 1s and a 3p, so this will be basically in the px, this will be an x. So this will overlap with this to give you this. And this is a bond in hydrogen chloride or hydrochloric acid molecule. And the bond that you get here are sigma bond. Now, not one thing, I'm sure you get to understand as we proceed, is that an s orbital is only able to form a sigma bond. We'll look at one other type of a bond as we proceed in details. For now, we look at each one at a time or step by step. Okay, another type of overlapping that you have is a P and a P overlapping. So a P and a P overlapping. Now note that the definition of a sigma, you have an end-to-end overlap. So there's this end and this end overlapping to give you a molecular orbital like this. And what you should note is that if this is a 2px, this should also be a 2px because they should become in the same axis for them to be able to overlap. So a px can only overlap with a px on the end to end to give you what you might refer to as a sigma bond. So overlapping of 2p orbitals is directed along the bond axis, meaning it only takes place along the axis. Then what results is a sigma bond. So this gives you a preview on how atomic orbitals will overlap to give you a molecular orbital. And in most cases, what you get as a molecular orbital is from the three concepts that we've looked at, from an S and S, an S and a P, and a P and a P, all will result in what you refer to as a sigma bond. Then one key point to note is that an S orbital is only able to make an S. So it is only able to make a sigma bond. Let's dig deeper into what you might do as hybridization. Now, what is hybridization? Right? I think in the first slide we've defined what hybridization is. Hybridization is combining of two valence atomic orbitals to form a hybrid orbital. So you have orbital number one, orbital number two combining, then they form the hybrid orbital. So now what you get is that from the previous concept, we know that molecules bound together by sharing electrons between orbitals. Then we use the Lewis concept to arrange the electrons to electron pair. Then after which we use the repulsion theory to predict the shape of the molecule. Then now what we get is that hybridization describes the formation and the properties of atomic. So when you're talking about hybridization, what you're talking about is you're talking about basically orbitals. Hybridization talks about orbitals. The Lewis dots theory does not consider the orbitals. It only considers the valence electrons. Now, here is the difference. Hybridization consider both the valence electrons, so it considers the valence electrons and the valence orbitals. The first concept only considers the valence electrons. So now let's take our example, methane, right? Let's look at methane as our example. So now what you get from methane is methane, the chemical formula is CH4. So there are two atoms here. There's carbon and hydrogen. Then you know hydrogen has one s as valence atomic orbitals, and carbon has two s and two p as valence atomic orbitals. Now, how do these interact to give you a hybrid orbital? Okay, so you can see for carbon, then note that only the central atom undergoes hybridization. So meaning when you have CH4, carbon will be the central atom. So it will be only carbon that undergoes hybridization, and hydrogen basically will not. So in this case, we will look at the properties of carbon. Then note that in carbon, there is a 2s and 2p. Then p's, there is a px, py, and pz. So meaning there's 1s and 3p's. So this is what you get. You get 1s and 3p's, like that. So now, how do we use this orbital to form a hybrid orbital? Now, one thing you should note is that you have one s, sorry, two s, there's one. Then the two p's, they're basically three. So if you combine 1 plus 3, it will give you 4 orbitals. So when the 2s and the 2p form hybrid orbitals, what you get is basically 4. And the geometry, as we saw in the previous slides, is basically a tetrahedral shape, and all the bonds between the carbons will basically be equal, and they have equal energies. So now what you get is what you have here. I know this seems to be a bit complicated. So in terms of the structure, what you get is that you have 1s combines with the 3p's, and this is how the hybrid orbitals basically look like. So you can see that this has increased in size a bit, this has increased in size a bit, this has increased, and this basically has increased. And what you get is that if you draw the energy diagram, let's say this is a change in energy, meaning energy is increasing upwards. Then you know that the 2s has lower energy as compared to the 2p's. So this will be an orbital representing the 2s, and this will be orbitals representing the 3 p orbitals. Now, what you get is that we know from electronic configuration, we have for carbon 1s2, 2s2, 2p2. So these are the valence electrons, and this is what we are considering here. So you know that in the s, there are 2 electrons, which are these. So there is one with an opposite spin. Then in the p, there are 2 electrons as well. Then you know, according to Hans' law, they first have to be singly filled. So you get one like this and the other one like this with opposite spins. So what hybridization talks about is that the 2s and the 2p will combine. They will interact. And how is that interaction? That interaction will basically cause this electron to be promoted to this empty orbital. And what you get are 4 equivalent hybrid orbitals. Now you can see this has lower energy and these have higher energy. But the hybrid orbitals have the energy which is neither for the s nor for the p. They have 4 equivalent energies. This is 1, 2, 3. And each one of them will be singly filled, singly filled, singly filled, singly filled. And these, since they are formed between 1s and 3p, so you have 1, 2, 3 there, what you get is basically called an sp3 orbital. So an sp3 means you have one s plus 3 p's giving you 4 sp3 orbitals. And that's the hybridization in methane. So from here, what you see is that since there's one electron here, another electron there, another electron there, what it means is that carbon now can receive an electron in this point from hydrogen. It can receive an electron from here from hydrogen, an electron from here from hydrogen, an electron from here from hydrogen. Now, since hydrogen can only contribute a single electron, so meaning there will be 4 hydrogens to accommodate all these empty orbitals. So in regards in talking to hybridization, in methane, this is hybridization. It's an sp3. It's easy. An sp3 is formed by combining a 2s and 3 2p's. Then you have 1s, 3p's. When they combine, they give you 4 equivalent hybrid orbitals. Now it's a hybrid, meaning it's in between. So the energy is neither for the energy is slightly above the s and slightly below the p. So it's an average that you get in terms of energy. So what you have is that this is what you get as your hybrid orbitals. When one of the electrons gets promoted, these are basically your hybrid orbitals. And this, the 1s does not get involved in any chemical reaction. So the only ones that are involved are the valence electrons, which are basically these with the highest principal quantum number. So this is what we are talking about. So you have for carbon, there will be 2 in here, and there's one. This gets promoted to there, and you get 4 equivalent hybrid orbitals in methane. And note that hybridization is only taking place in carbon. More examples. There you go. So what will result basically is only this. And one key principle that I need to highlight is that hybridization only takes place in the same principal quantum number. So for example, you have 1s2, 2s2, 2p2. Hybridization will only take place between the quantum number n is equals to 2. Remember, according to the definition, it only deals with the valence orbitals. Then you know that valence orbitals are occupied by valence electrons. So according to this, then when you use the repulsion theory, what you get, since there are 4, what it means is that carbon will have the shape of a tetrahedral. So this is a point where it meets with a Lewis dot structure. So when it comes to predicting the shapes are actually quite similar, except for if you talk about water. Water is a tetrahedral, but the dot theory says it's a bent, like it's a bent. It forms a V shape, but it's a tetrahedron. Let's proceed. We look at hydrogen. So we look at ammonium and valence bond theory. So the valence bond theory is one that explains about the hybridization, which is abbreviated as VBT. So meaning valence bond theory. So same applies in here. You have NH3. So there is N, which is nitrogen, nitrogen 7, 14. So the electronic configuration of nitrogen basically will be 1s2, 2s2, 2p3, right? Carbon, hydrogen has already been established. You have 1 there, so it's just 1 like that. Then when you talk about hybridization, it's only the central atom, so meaning only nitrogen will undergo hybridization. And since we are using valence electrons, so it is only in there. Now, let's put things, we use the similar principle that we've looked at. Let's draw the increase in energy. So this is a change in energy. Then you have the 2s and basically the 2p. So you have 1s, 3 p's. So when it comes to occupying the electrons, what you get is you have 1 here, 2, then 1, 2, 3. So what you have is that these four orbitals will combine to give you 1, 2, 3, 4. So first, now you check there are 4 sp3 hybrid orbitals. The number of electrons are 1, 2, 3, 4, 5. So there are 5 electrons to be filled in the 4 hybrid orbitals. So what you get is that the first row is singly filled. So you get 1, 2, 3, 4. Then there's a fifth. The fifth now will go in there. So now what you get from here is that this will give you what you normally call as a lone pair. Then this can receive an electron from hydrogen, an electron from hydrogen, an electron from hydrogen. Since hydrogen can combine one electron, so many only 3 hydrogens will react with the nitrogen. Therefore, the formula of ammonium will be NH3, like so, or like this. Okay, so these are from hydrogen. And note that the bond angle in is 107. Now you know that an ideal tetrahedral is 109. So what it means is that this is like more or less like 2 degrees away from an ideal angle. Now the question is, how do you explain this? The answer is very simple. Ammonium or nitrogen has a lone pair. Then you know from here is that lone pair, lone pair diffusion are greater than lone pair, bond pair, greater than bond pair, bond pair. So in short, nitrogen, if we look at the structure, what we have is that nitrogen will have a lone pair. So there's a lone pair here and a bond pair, bond pair, bond pair. So what you get, there's this repulsion there, this repulsion there, and this repulsion there, and this repulsion there. Now, not let's say this is A, B, C, and D. We know that A is lone pair, lone pair. B is the same. C is a lone pair, bond pair. D is lone pair, bond pair. Then we know that these are greater. So meaning A and B will have greater repulsion as compared to C and D. What does that entail? It causes the molecule to squeeze these angles a bit because the repulsion between A and B are greater than C and D. So what it is that it will be pushing a molecule a bit further in that direction. It will be pushing the bond further in that direction, and it only achieves that by 2 degrees. That's why if you notice in ammonium, the bond angle is 107.2, and in an ideal tetrahedral is 109 degrees. Okay, still looking at shapes. So now what you note is that one thing you note is that when these three combine, they actually combine to give you this molecule, and this happens at the same time because uh, the px, the py, and the pz, they all exist at the same point. Then when they form hybrid orbitals, this is how the hybrid orbitals will look like. So in reality, the sp3 looks like this. So there's a center here, and there's an orbital there, an orbital here, an hybrid orbital here, hybrid, hybrid, hybrid. Then what you have is that this is now 109.5, 109.5, 109.5. uh, throughout. Okay, still looking at further examples, this is what will happen. Now, this contains 4 hybrid orbitals. So you have 4sp3 orbitals. So there's 1, 2, 3, 4. Each one of them having a single electron. So meaning we know that an orbital can accommodate a maximum number of 2 electrons. So if an orbital has a single electron, meaning it can receive 1 electron. So now what you get is that this will receive an electron from that, this will donate an electron from this from that, and this from that. And this is the shape of a methane molecule. Then note that the bond angle here is 109.5. The reason being, methane hasn't got any lone pairs, so we only have bond pair repulsion. And when these are repelled equally in 4 directions, what you get is a tetrahedral with 109.5 degrees as your bond angle. All right, let's look at molecules that have lone pairs. Now, it's the same concept that you get. We've established on methane, and this is how it basically looks like. Now, note methane is not like this with 90 degrees, 90 degrees, 90 degrees, 90. No, 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 no. Methane is shaped like this with 109 bond angle, like everywhere else is 109. Same applies if you look at ammonia, this is 107 because it has a single lone pair. Now we can look at, I can give you an example for water. Then after which we see why water has a lower bond angle as compared to the others. Now, water is H2O. So there is oxygen and hydrogen. We know hydrogen is 1s1. Then oxygen is basically 1s2, 2s2, 2p4. So water is 8 and 16. So there are 8 electrons in water. Then we know that the valence electrons are these here. So meaning in the principal quantum number 2, you have valence atomic orbital occupying the valence electrons. So from there, what we have is that let's say this is an increase in energy, change in energy like this. So there's 1s, so there's 2s, then there's a 2p. So this has 2 electrons, and this has 4 electrons. So what you get is that this has 2, 1, 2, 3. So this is 1, 2, 3, 4. So when these 3 combine to give us hybrid orbitals, you get 1, 2, 3, 4. So this is sp3. So now what you have in here, in the total number of electrons, you have 1, 2, 3, 4, 5, 6. So there are 6 electrons. So first they'll be singly filled. 1, 2, 3, 4, 5, 6. So in short, in water, what you're talking about is that this is a lone pair and this will be a lone pair. So lone pair, 2 lone pairs, and this is what you get. There's a lone pair here and there's a lone pair. Now, the repulsion between this is greater than that and that, this and this. So meaning the bond angle in water, which is between hydrogen, oxygen, and the hydrogen here is 104 degrees, meaning it has been squeezed by roughly around 5 degrees because of the lone pair. So the lone pair repulsions are higher, so it will push the molecule outward further than it is supposed to be. Okay, let's look at other aspects of hybridization. Now, what we were discussing was an sp3. Let's look at an sp2. How is an sp2 formed? The concept is quite similar, but in this case, you have 1s plus 2 p's. So they give you an sp2. So since it's 1 by 2, so you get 3, 1, 2, 3 as your energy levels. So this is what you get. Let's look at our example, which is basically ethylene. Now, Ethylene is an sp2. So what you get is that you have one S interacting with the two P's, only this and this. So the interaction is between these three. Then this does not get involved in the hybridization. So it will remain. So you can see the energy of this is the same. So this remains as a pure P, and these are hybrid orbitals. So what you get is what is shown here. So in the ground state of carbon, this is what you have. When it interacts, you get this. So you get three sp2 hybrid orbitals and one pz pure orbitals. So now from here, what you get is that three psp orbitals will be, there's one like this, there's the other one here, and there's the other one here. Now note that this has a single electron, this has a single electron, and this has a single electron. Also, this has a single electron, but this is a pure P. So it is pure, meaning it has not gone hybridization. So now what happens is that these hybrid orbitals, for example, the hybrid can interact with one another like this to form a sigma bond. Then you know a sigma bond is a head, so it's a end to end. Now, adding a new concept to that is head to head, meaning in that direction. So this is what it means. So this is the head like this, and this is the head, and this is basically a head. So what you get is that you have this will be a sigma bond. Then now when these interact, what happens is that the pure P will come close each other parallel to the sigma bond. They are at 90 degrees to a sigma bond. So they will also tend to overlap on what you might refer to as a side to side. So a side to side overlap is what you normally call as a pi bond. Now, one thing that you should understand is that a pi bond will never exist in isolation. It don't take place on its own. It only takes place after a sigma bond has been formed, then a pi bond will also be formed. So a sigma bond is a head to head. So what you get is that if I was to use simple structures, let's say you have this and this. So this is an sp2 and sp2. This is a pure P and this is a pure P. So first this will interact on the head to head to give you a sigma bond. Then when these two interact to give you a sigma bond, they will bring the pure P and the pure P close to one another. So they will also interact like this to give you a pi bond. So when you talk about a sigma bond is a head to head, and a pi bond is a side to side overlap. So now we can consolidate this concept. We know that in chemical bonding, there are two types of bonds. There is a sigma bond, abbreviated as that or symbolized like that. Then there's a pi bond, abbreviated as a pi like that. So this is side to side, and this is head to head overlap. This is now what happens in an ethylene. So in an ethylene, you have head to head, head to head, head to head, head to head, head to head. So what you get is that it will form a sigma bond, one sigma bond, and a sigma bond. Then after it interacts like this, it brings the pure P close to one another to give you the pi bond. Then you can see there are two electrons that are being shared here. Now remember, we said in an overlap of chemical bonding, the electron density is in between the two atoms. So this is a carbon atom and this is a carbon atom. Then the electrons are between the carbon atom. Then this is a carbon atom and this is a hydrogen atom. The electrons are between the hydrogens and the carbon. So the hydrogen and the carbon over there. So the shape of ethylene will basically look like this. Now, what will be the geometry? Now, two things that you need to note is that on ethylene, since it has a double bond like this is normally planar. And what you have here is 120 and it's a triagonal planar. Triagonal means it's three, separated by three. So meaning is 1 here, 2, 3. Then the bond angle is 120 degrees. So putting the picture into perspective, this is what you have. So these are the pure P that are forming a sigma, and this is how the sigma looks like two sausages like this, and the other one basically like that. Okay, she's explaining the same things there. So sigma, 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 sigma. So a sigma between a carbon and a carbon, and a sigma between a carbon and a hydrogen, carbon, hydrogen, carbon, hydrogen, carbon, and hydrogen. Then when you bring these into proximity, this is what you get. So the pi bonds will be like this, and the sigma in the center. So sigma, 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 and sigma. So this illustrates to you on how the double bonds are basically formed. Note one thing, that a pi bond does not exist in isolation. So every time you say pi bond, there should be a sigma bond somewhere. That's why a double bond will be first be written like this. You have carbon like that, then another sigma like this to give you a double bond. Okay, so you can see that between the hybrid orbitals here, the bond angle is 120. Then between the hybrid orbitals and the pure, the bond angle is 90 degrees. They're perpendicular. The hybrids, the sp2 and the pure p, are perpendicular to each other. So perpendicular, it means the hybrids will go onto head to head, making the one that is perpendicular to them go on side to side, as it is shown like this. So this is what you get: sp2, 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 and sp2 everywhere. So all the bonds in ethylene are basically sp2 types of bonds. Okay, we've defined already what a sigma. A sigma will take place along the axis in the head-to-head fashion, and a pi takes place below the internuclear axis on the side-to-side fashion. So sigma will be head-to-head, and pi, so head-to-head, and the pi will be side-to-side. And this is basically what you get. So it's head-to-head and side-to-side. So these are side-to-side, and these are coming on the head-to-head. So the geometry will basically look like this. So part A is the orbitals used to form the bond in ethylene. Then here it's a Lewis structure to illustrate ethylene. We go to another concept that you normally call as an SP. Now I'm sure by now we've established full well, or you understand how an sp3 comes about, an sp2, 3, and now an sp. So an sp, you have one s and one p, giving you two sp orbitals. So in the similar way, change in energy. Now note that from here, the 2 appears lower because there's lower energy, and this has a high energy. So what you get, there will be interaction between this and one of that to give you sp, sp. Then these two will remain as pure p orbitals like that. And this type of hybridization takes place in carbon dioxide and also in a triple bonds. Okay, so this is what you have. So in sp, you have two sps and two pure p. So what it means, this can make one sigma, and what the result is a triple bond. Now in an sp3, now note that hybrid orbitals are the ones that determine the geometry. So it is like this. If you have four hybrid orbitals, you get four sigma bonds. So this is a tetrahedral. Three hybrid orbitals, you get three sigma bonds. This is a triagonal planar. Two hybrid orbitals, you get two sigma, and this is a linear, meaning this is 109, 120, and this is basically going to be 180 degrees because it's linear. It's a straight line. So you have a carbon here of that and that. So this is 180 degrees. And when you draw the structures, this is how they will look like. So in a 108 degrees, they'll look like this. Now note that this will overlap with that to give you these two hybrid orbitals. So now these two exist, this and this exist at the same time. So what you get is basically that as a structure. Then when you put things into perspective, this is how it will look like. So this is an SP and SP. This is a pure P and a pure P. So meaning this can go into head to head, head to head. So the head to head are the one that determines the geometry. Then this can go into the side to form one pi bond. This can go into the side to form one pi bond. And this is what happens. The first thing is the ones that forms the head to head like this. Then you have now two pure P. So there's one pure P like this going that way and that way. Then you have this going that way and that going basically that way. So now what you get is from here is that you get two sigma and two pi bonds, and the geometry will basically look something like this. So it will look something like that. Then when you look at the geometry in water in oxygen, this is how basically it will be. So oxygen, the hybridization that it will undergo is an sp2, and you have head to head, then sigma, sigma. So this is what you get in terms of carbon dioxide. So carbon dioxide, there's this is a sigma and a sigma, then that's sigma, and basically that's a sigma. Then note that there's if you go to the next slide, these are head to head. And since carbon has two pure P, there's one pure P there and the other pure P there. So this will interact with that one and this one will interact with this one. So now what you get is that it will form two double bonds. So you have oxygen, something like this. So you have something like that. So this is basically how it will look like. So you have these are head to head, then these are now side to side to give you the chemical formula of azide is basically like that. Okay, a sigma and a pi bond. How many sigma bond and pi bond are in acetic acid? Okay, the structure of acetic acid is given like this. So in acetic acid, let's see, there's 1, 2, 3, 4, 5, 6. So there are 6 single bonds. Then note that all single bonds are sigma. Then we go to the double bond. How many double bonds? There is one double bond. So one double bond is formed between one sigma and one pi. So since there's 6 here and 1, so the pi bonds, the sigma bonds are 7, and the pi bond is only 1. Okay, so this is what you get. So you have 6 sigma bonds plus 1 on the double bond, giving you the number 7 as a total. Then you go to a double bond as 1 pi bond, and this gives your answer as basically 1. Okay, so in just try to compare or understand what a sigma bond. A sigma bond, so a pi bond is a side to side, so they will hit from side to side like this. Then a sigma bond is a head to head. Note that for overlapping to take place, a pi, so an atomic orbital should have a single electron. So one electron, one electron. So these two overlap, they give you these two electrons, which are a sigma bond. So one electron here, one electron. So these two overlap, they give you two electrons. This is basically a sigma bond. All right, in view of that, I think I'll end here on these lectures and I'll continue in the other series of lectures. Thank you very much.